So next up is Cluosh with Shader Frenzy.
Hello everyone, I'm Cluosh and welcome to Shader Frenzy. A little bit about me. I'm a student at the Vienna University of Technology, a member of the Wionio CTF team, and I'm usually working on finite element visualization. That's why I got interested in doing a little bit of a graphics talk and not a security talk. So yeah, that's my background. Before we start, I'm sorry that the speaker desk is kind of in the way, so I can't see you people on the other side very well. I hope this is not going to be a problem. The other thing is I prepared some stuff on shaders.cluosh.net. You can find the slides there. And most importantly is this link here to the Book of Shaders. This is an editor where you can edit GLSL code in your browser. So you can follow the code examples and try it out on your side. And the code snippets I'm going to use are listed here. They're grouped with the topics, and I'm going to use them and change them a bit, and we're going to try out some stuff. So to everyone wanting to join, can you access the website and the editor? Is this working out for everyone? Oh, wait. Here. I'm sorry I didn't include it in the talk description. It wasn't there at the time, but okay. So, what are we going to talk about? I'm going to do a little bit of an intro. What is OpenGL? What can you do with OpenGL? What are we going to do with OpenGL? Specifically, how you get some color on the screen, how you change the colors, through time. Yeah, speaking of change, how can you perform change that is updated live without user input, with user input if you like it. We're also going to talk about how you can draw simple shapes, or what you need to do to draw shapes. A little bit on the math side, because a lot of stuff in computer graphics is related to math. I'm going to try to keep it simple. I can't promise it will be simple, but we don't really need to understand the math. We can just use it. I'm going to talk a lot about ray marching, because this is a really powerful technique. And I hope I can spend most of the time talking on this. But since it requires all of the other knowledge of the other topics, please ask questions as soon as possible, so you can follow the examples later on. Because it's going to be really hard if you don't understand something in the beginning, because I'm not going to explain it a lot later on. So yeah. I'm going to do a short example on how to get a bit of randomness into the shaders. Not much. And if there's time left, I'm going to talk a bit about the demo scene. I'm not in the demo scene myself. I'm just starting to get into it. just giving you some information on why you might get into it or how you can get into it. So, what is OpenGL? OpenGL is an API that lets you access your graphics card. Usually the graphics cards have their own instruction sets and vendor-specific commands. And the OpenGL is just an abstraction above the graphics driver, which lets you control the graphics card. One example of what you can do with OpenGL and what is done with OpenGL is, for example, games. That's a screenshot of something I created for university. It's not really that interesting, but it's one example of what you can do with OpenGL. You can see you have this background. You can do shading and lighting. And that's what I do for work. Is finite element visualization. You process a model, like a crankshaft in this case, with some physics solver, and then you need to visualize the results. So this is how I initially got into the shaders. And this is a rather simple example of what you can do, because this is just assigning colors to pixels depending on some value. So how does OpenGL work? If you've ever tried to draw something without OpenGL, you might have started something like a loop, looping over every pixel of the screen or the window, and then setting your pixel color depending on some conditions. OpenGL works quite differently. You have a pipeline in OpenGL starting with some vertex data. This means you can build a 3D model, and the 3D model is encoded in nodes, your vertices. Each vertex has 3 coordinates, x, y, and z. And additionally, you have to specify which primitives do you want to draw. In new OpenGL version, the only thing you can draw is triangles. So you have to split your 3D model into triangles. Then once you have processed the data, it's going to be passed to a vertex shader. The vertex shader is a program you specify, and it's doing the transformations on the vertex data you sent to the graphics card. And the vertex shader is transforming the vertices and is passing the data to the rasterizer. The rasterizer in OpenGL now checks which triangles are visible and tells the next step in the pipeline, you might want to draw something there. And the next step in the pipeline is the most important part. It's the fragment shader. This is doing the coloring. So we have the vertex data, the shader, the rasterizer, and now we know where the vertex, the fragment shader knows where to draw, and you need to tell it what color do you want it drawn. And after that, there's some other stuff applied, and the image is going to be displayed on the screen. So for the purpose of this talk, we're going to skip all the other steps of the OpenGL pipeline. But we're going to focus on the fragment shader, because in the recent times with WebGL and things like ShaderToy, we can code fragment shaders in the browser without having to care about the initialization of OpenGL. So we don't have to set up the boilerplate code. We don't have to load any 3D models, pass any vertex data. We can just focus on getting the color on the screen. So how do fragment shaders work? As I explained earlier, if you tried to write a drawing program without OpenGL, you might have looped over the screen and did something to each pixel based on some conditions. A fragment shader now is a program which calculates the color of one pixel. The thing is that this is independent from all the other pixels. So this program is going to be run for every pixel on the screen. So if you have a lot of pixels, this is going to be expensive. And that's why you would usually do some of the other stuff in a vertex shader or in the prior OpenGL steps. But if you're only using a fragment shader, you can do all the stuff there. It's going to be expensive sometimes. If you keep it simple, it's going to run smoothly. But yeah, the thing is, because the program is called for each pixel independently, you can execute this in parallel. This is why graphics cards are so fast, because we can process all the stuff in parallel without caring what else is happening to the neighboring pixel. In our case, it also means we're going to have to do a lot of recalculation, but because of graphics cards, it's still going to be faster than relying on the pixel beside you. So we're doing the pixel coloring independently. So how does the OpenGL shading language look like? Let's get to some editor. Is the font size big enough? Can everybody read? Okay, fine. Let me copy this. So there's a bunch of stuff happening already. Don't worry, I'm going to explain everything. This is just to give you a brief overview how the shading language looks like. It basically looks like C, but we have the most important difference is that we have vector data types, like vec2 stores a vector with 2 elements, and we can access vector elements. We can use it like normal variables. We can do calculations as if it were a single value, and we can access values from vectors by using .xy, for example, to access the x and the y coordinate, which is going to give you a new vector of 2 elements. This is called swizzling. So if you want, for example, a vector t, and you want just this variable right here, and you just want to flip the coordinates, you can say fraccord.yx, for example. Or you can say you want a vector with both the elements being the y coordinate. You can do y and stuff like that. Is anyone here who never programmed any C-like language before, or? Okay, so I don't need to explain if, branches, and variables. Good. This part right here, I'm gonna explain it once, and I leave the explanation out for the rest of the time. Some GL implementations require a precision statement for the floating point types, because we can have floating point types with a different precision, especially with graphics card support. This can speed up calculations if you use a lower precision floating point type. This might also cause artifacts in the rendering. So it's a trade-off if you want to use lower precision floating point types, higher precision floating point types. But yeah, it also depends on your graphics card. If it even understands that you want a different precision, most graphics cards, like mine in the laptop, is probably just going to use one precision for everything and ignore the precision statement there. So this part is just going to be there in all the other shaders, and it's not going to receive any further explanation. So, what would our first fragment shader look like? You can try this out in the Book of Shaders editor. It's the first code snippet, and it just has a void main function, and it assigns a value to the glfrag color variable. The glfrag color variable is our main color output. This means whatever is in the glfrag color variable at the end of the shader execution is going to be the color on the screen. How do we specify colors? We use RGB, and all the values are going to be between 0 and 1. So we have a vector of 4 elements, which means we're still missing one, and this is going to be the alpha value, which is going to be mostly 1 or 0. We don't have alpha blending enabled, and it's not going to make much of a difference. So we can basically ignore the rest of the vector. So if we want to color the screen red, for example, we can set the first entry to 1. Just leave the other ones at 0. The cool thing about the Book of Shaders editor is if you click on a WEC4, for example, like this, you get a color wheel. You can just change it on your screen without having to type in the values. This is pretty comfortable for trying out different values for stuff. It's one of the reasons why I chose the editor for the presentation. So, in the previous shader, we had uniforms. Uniforms are parameters specified by the calling program. In our case, we don't specify any of this. We can just use them. If we had to write the whole OpenGL boilerplate code, we would have to make sure all the values are going to be passed into these parameters. The Book of Shaders editor has these 3 parameters you can use. It provides us with the resolution of the drawing canvas. It provides us with mouse position, so you can do some mouse interaction stuff by using the mouse parameter. And most importantly, it supplies us with the time in seconds. So if we go ahead and use the resolution uniform, is specified like a normal variable. Instead, you could do it like this, but the uniform is the important keyword. So the uniform tells the shader it's going to be supplied by the calling program, and we don't have to care about it any more than that. And now we can use the resolution. Since our drawing canvas has different resolutions on different screens, we might want to convert the coordinates we get into the shader by normalizing them to the screen resolution. And we can do that through the glfrag coord. The glfrag coord is the coordinate of the pixel you're currently processing. This means it's the identifier of the pixel you're currently working on. And you can normalize this to the screen by dividing it through the resolution. So what happens here is you're dividing the coordinate you're using through the resolution, which means you're gonna put the values in a range from 0 to 1. Now you can do stuff like this, where you say if the x-coordinate is smaller than 0.5, you color the screen, the left side of the screen, with the color we specified. What we're going to do in other examples is we're going to scale this to 2 and shift it by 1. So we have the origin in the center of the picture, which is going to be nicer to handle for other stuff. But it depends on what you want to do. We're going to do it this way for now. So what can we do to bring shaders to life? Right now we're just drawing some color, some fixed color, depending on some values. What we can do is we can use, for example, the user input through the mouse uniform, or we can use the time from the time uniform, which we can then use to do some kind of periodic change in the shader. And we can later use it to introduce some randomness. Okay, so I'll show the time example here first. You can now do stuff like this. You can use a sinus with the time parameter, and now the color is going to change based on the time value. So this is just a simple fade. And now we're going to use the second snippet, the intrinsic snippet. Oh, it's the third one, really. So what the intrinsic snippet does is it scales the display so we can see a function, and it draws this function, in this case the sinus. And now we can try the different shader intrinsics. Intrinsics are the functions already provided by the shading language. Sinus is one of them. We can do a cosine. We can do a tangents, a logarithm. The code down here is to make sure we can see the function. This is actually, the code down here is actually drawing the function. And I'm gonna explain this in a bit, what the step function does. But for now, you can just try out some of the intrinsics. I have a link to the WebGL reference on the shader side, and it has a complete list of all the stuff you can do. It's important to note that all of the trigonometric functions are using radians and not degrees, but there are conversion functions supplied. So you can easily convert between radians and degrees. We have all kinds of exponential functions. We have some common functions which are really useful: the absolute value, the floor, ceiling, the fractional part, min, max, clamp, which is just a combination of min, max for readability reasons. with mix, we have step and we have smooth step. And those two functions, the step and the smooth step function, are going to come in handy when we're going to draw shapes on the screen. Is there anything else? Yeah, also important is the length function, which gives us the length of a vector. Yeah, so the step function does the following. You specify a threshold, and if you're below the threshold, the step function will give you a 0, and if you're above the step, you get a 1. So you can make hard edges with the step function, or you can use the smooth step function, which gives you an interpolation, where you specify the lower border and the upper border, and then it's going to interpolate on the way. So it gives you a smooth edge. I personally prefer the step function with the hard edges, but it depends on what you want to do. So let's start with the circle snippet. You can see the step function in action here. If we comment out the second line, we're getting a full circle. The simplest way to display a circle is to just use the length of the normalized coordinates. Make sure they're below some radius. So maybe I can draw this somehow. Let's try it out. Okay, good. So we have our coordinate system, which we centered in the screen. So our screen center is 0, 0. And now we have some pixel. We know we're at some pixel in the shader, and we know its coordinates. And since we centered the whole coordinate thing, we can just calculate the vector from the starting point, from 0, 0. This vector is just our coordinates since we're centered it. Now we're going to calculate the length of the vector. And if we do this for every pixel on the screen and check if the length is below some certain value, we get a circle. Yeah, it looks better on the shader. But now you can do the same thing with the step function in the other direction. You can say the length of the normalized coordinates is used with the step 1.0, and then you're going to have a radius of 1, and this is going to be I think I switched it. So you have the first value is the actual threshold, and the second value is the value you're testing against. So No, I'm a bit confused. I have to check. Yeah, the first value is the threshold. So the first value is in this case our radius, and we're checking it against our length. And if the length is below 1, the step function gives us 0. And if it's above 1, it gives us 1. And so we can check the value of the step function with an if statement and compare it, for example, with 0.5. And if you add a second step function with a smaller circle, you can subtract it from the original step. No. So in this case, I kind of messed up the order of the operations. But if you combine the step functions with the correct arithmetic operations, you can produce shapes like this where you just cut out the inner circle by subtracting it, for example. Also, if you haven't noticed, you can either initialize a vector by specifying all its values, or you specify a single value which is going to be used for every component. You can also initialize, for example, a vec4 with a vec3 and an additional value. So you can either specify all values, a vector and an additional value, or one value. So how does this work if we want to draw a rectangle? Again, you draw the rectangle by combining the step functions. You can start with making sure that the first part of the screen is blacked out, meaning everything lower than a certain x coordinate is blacked out. Then you're going to multiply this value, since it's either going to be 0 or 1, with the step function blacking out the other part of the screen. Then you're subsequently blacking out parts of the screen until you get a rectangle. That's the method I used to draw the letters in this shader I posted on Twitter a few weeks ago. You can put this to the extreme and draw every pixel of the letter with a rectangle like this. You can also use polar coordinates for shapes, meaning you calculate the vector, the radius from the center of the screen, which is just the length of the vector again. Then you can calculate the angle of the pixel to the center, so the angle between the x-axis and the actual pixel vector. And then you can use, for example, the cosine to draw stuff like this. Then you can use again the shader to change the values. So now we get to the fun math part. In OpenGL, it's common to use matrices for transformation, because all the points you draw are basically just vectors. And you can use matrices and stack the transformations in a single matrix and apply this to the vector. And since matrix multiplication is not commutative, the order matters. So it matters if you first translate an object out of the middle and then rotate it, or rotate it first and then translate it, because you're going to get totally different results. Yeah.
There's some operations that are like rotation and non-rotation.
Yeah, you can do this either way. So as long as you stick with the same type of operation, it doesn't really matter in which order you execute this. But if you, for example, the rotation needs some kind of pivot, and by default, this pivot is always the origin. So if you're just going to rotate, you're always rotating around the origin. And if you're translating, you're moving the origin basically, and then the rotation is going to end up in a different place. So how do those matrices look like? We have the scaling matrix, which is the easiest matrix, because you're just using an identity matrix and use the scaling factors you want to apply on each coordinate in the diagonal. So you have your x scaling factor, your y scaling factor, and your z scaling factor. And when you multiply that with your point, in this case, this is our point, you'll see in a moment why it has 4 entries and not just 3. So the x is going to be multiplied with xs, and the y is going to be multiplied with ys, and the z is going to be multiplied with cs. The reason we have 4 entries in the point and the 4x4 matrix is that in a 3x3 matrix we couldn't do the translations, because everything would be multiplied with x, y, and z, but we don't want to multiply the translations with anything unless we specifically specify it. So we include another additional value, the 4th parameter, which is 1 in this case. So instead of being multiplied with any of these, it's going to be multiplied with 1 and added to the vector. So I think the hardest part are the rotation matrices. I'm not going to explain how you get to this matrix, but it's there, and you have 3 different matrices for x, y, and z axis. And you can use this to do transformations. So let's get to the transformations snippet. So here we have a rectangle. We're not drawing the rectangle like before. I'm using a sine distance function here. I'm going to explain what sine distance functions are soon, but for now we just leave it here. I've implemented some operations for scaling, translating, and rotating around the z-axis. What is important is that GLSL uses column major notation. So what you see here is not a row in the matrix, but a column. So we have the first row, the first column in the first row, the second column in the second row, the third column in the third row, and so on. In the case of the scaling matrix, it doesn't matter. But when we come to the translation matrix, which we saw in the slides, would have the coordinates here in the last column, we have to specify the translations in the row, in the last row. And the rotation matrix for rotation around the z-axis is not that different from the x-axis. It's basically just swapping around the cosine, the sine in the correct place. Yes. So we can try applying the different transformations here. For example, we can scale it. We can translate. We can rotate. We can also try stacking the transformations in a single matrix. Let's say scale vec3 0.8 times rotate z. And then apply this. Now we have it scaled and rotated. This is pretty nifty. And you can use, usually you'd do these kind of transformations in the vertex shader, but since we don't have a vertex shader, we're doing it here. So, now that we've got the transformations covered, we can proceed to signed distance functions. So, what we've drawn now were 2D shapes. We haven't really talked about drawing 3D shapes yet, and the signed distance functions are going to change that. Now, a signed distance function is a function which gives us the distance to the surface of a volume. So if we have a function, a distance function of a sphere, it's going to tell us how far are we away from the sphere. And if we're inside the sphere, it's going to give us a negative value. So we have a positive distance for the outside, and we have a negative distance if we're inside the sphere. So the negative distance would tell us if we're inside the sphere, how far is it to the surface. In mathematical notation, the sphere signed distance function would look like this. We have a center of the sphere, C, and we have a point we want to check against. And we would subtract them and calculate the length, and subtract from this value the radius of the sphere. Simplified, if we're doing this around the origin, we can just leave out the C. This is nice because we can just use all the sign distance function without any notice of origin and use our transformation matrices to move them where we want them. Since mathematical notation isn't as nice, the GLSL notation is a little bit clearer. You have the parameter vec3. This is your the point you want to test against. And you just do the length of the point minus 1. Minus 1 being the radius. So let's see if I have a snippet for that. Yes. So this is basically the same as before when we first wanted to draw a sphere. But this time it's just a little bit refactored to use a sign distance function, which we have been using implicitly before, but this time it's really a sign distance function. And we're using our normalized coordinates as input for the sign distance function and test if we are below a certain threshold. Because if we're lower than 0, we're inside the sphere, and we want to know when we're just above the surface of the sphere, just a little bit this epsilon value. Also, the sphere is now actually 3D. You don't see it yet, but it's 3-dimensional. So how do we make it 3D or make it look like 3D? We're not going to use ray tracing, but the example, what we're going to use is basically using the same principle as ray tracing. Ray tracing is tracing the path to and from a light source to color the object with the light and the shade, which we're not going to do like that. But what we're going to take from ray tracing is we have a camera, we have our image, this is our screen plane, and those squares are our pixels. We're going to calculate the direction of the viewing ray and intersect this with the sphere, or we're going to step along the ray until we reach the sphere. The difference now, what we're using compared to ray tracing, we're going to use ray marching, is ray tracing works on a lot of different geometry, but we're using sign distance functions. We don't have to step a specific value along the viewing ray. We can just calculate how far are we away from the sphere or from the next surface, and we just step directly to the surface. So this is pretty efficient, because in our case, if we only have a sphere, we just have to do one step, because okay, we know we're that far away from the sphere, and we just step to the sphere. It's gonna be more complicated if you add more than a sphere. You can combine the scene and add 2 spheres, a ground or something. Then you might get as the first value of the combined distance function something that is closer to the ground. And then you have to do a few steps till you finally reach the sphere. So what are we going to do with the ray marching? How are we going to do this? We first need to calculate what is the ray direction, what is the direction we're viewing at, since our camera is somewhere over here. We need to first calculate the direction from the camera through the pixel we're currently looking at in the fragment shader. We calculate the sign distance function value and move into the ray direction until we hit the sphere. So visibly nothing has changed, but a lot has been changed in the shader code. In order to do the ray marching, we first need to calculate the vector in which we're actually going to step the ray direction. The xy direction is relatively straightforward, since it's our x and y coordinate from the shader pixel. But we still need to calculate how far are we away from the screen. And we're using the tangents to do this calculation. Maybe I'll draw again. So what we want is so this right here is our viewing plane, and this is our camera. And what we want is this distance right here. And we can use this simply by using the field of view. The field of view is an angle we specify, and the alpha here is the half of that angle. So we can use the tangents again to calculate this distance through the field of view. Thank you. Now we have our ray direction, and we have a camera position, our starting point. And what we can do now is we can actually perform the ray marching algorithm. In this algorithm, we have a few constants. We have an epsilon. Like before, this is some small value, which is going to help us stay just above the surface of the sphere. We have a minimum distance for the algorithm and a maximum distance. Since GLSL doesn't allow you to run a loop for a variable number of iterations, you always have to have some kind of fixed boundary, some kind of maximum boundary of iterations a loop can run. In this case, we have maximum number of steps. So we can only execute this loop this number of times. But we can still exit earlier if you want. We just have to have some kind of upper boundary. So the ray marching algorithm works like this. We have our starting depth, which is 0 in this case. And then we're gonna calculate the distance to the next surface with the point I plus depth times the direction of the ray. So this is our camera position plus how far are we into the scene times the direction we're actually going at. And this is going to give us the distance to the next surface, the sine distance function. And now we check if we're below epsilon. If we've reached the surface, we return the depth. If we haven't reached the surface, we're stepping deeper into the scene by the amount we got from the distance function. And if we have reached a maximum, we're just returning the maximum and not caring about the depth. So now we get two things once the ray marching algorithm finishes. We now know which point of the scene did we hit. We know this P here is a point on the sphere, on the surface of the sphere. If it hit the sphere, if not, it's some point in the far distance. And we can check if we're past the sphere or if we're on the sphere by checking if we're bigger than the maximum distance minus epsilon. So if we get a depth value that is bigger than the maximum distance minus the small epsilon, we're outside of the sphere, we didn't hit anything. And if we're inside or on the surface, we get a 1. Now, this still doesn't look 3D. It's still two-dimensional from our viewpoint, because we still don't have lighting. We get the 3D look by actually applying light. And this is going to be our next step, which is going to involve some math again. In order to apply light, we need to know what is the normal vector of the point we hit on the sphere. Because without the normal, we can't calculate how much light is hitting the sphere at this point. And usually, if you have a sphere like that, and you want to calculate the normal, you could theoretically calculate this by using the derivative and calculate a tangential plane to the sphere using the derivative. But in our case, we can just use a point from the distance function slightly before the sphere and a point slightly inside the sphere by our epsilon, and can estimate the actual normal. Let's look at the lighting snippet. So this is already the complete lighting, but we can just look at the normal for now. The normal is calculated like this. We had our three vector components. We have x, y, and z. And we're evaluating the distance function slightly before the point with, we can do this by adding the epsilon to the x and subtracting epsilon from x and then calculating the difference. And do this for x, y, and z, and normalize this to a length of 1. And this way we get the surface normal of the sphere. Now we're far from done to get our lighting. What we're using is going to be Phong lighting, which means we have some ambient color. We're going to have diffuse lighting, and we're going to have a specular part of the light on the surface. And Phong lighting is calculated by a few things. So we have the ambient light, which is just the base color. There's no math involved. You just assign the base color. You have the diffuse color. The diffuse color is calculated by how much light hits the surface without actually involving the eye, our viewpoint where we are. How much light hits the surface is just calculated by the angle between the vector pointing to the light and the surface normal. So that's why we need the normal of the sphere to calculate how much light hits the surface. And when we use a dot product with the normal and the light vector, we get the cosine of the angle between them. And we can just use that as a factor for applying diffuse light. So we have a diffuse light color and multiply that with the cosine of the angle, which we get from the dot product. A bit harder is the specular light, which is calculated with respect to the viewer and deals with the reflection of the light. The specular light is the reflection. And we're using the dot product of the actual reflection vector and the vector pointing towards us. But we're not going to simply multiply this. We're going to do exponentiation. And apply the result of the exponentiation to the specular light color. So everything I explained happens here in this part. So we have our ambient color, our diffuse color, and the specular color. And we start off with our ambient color, which is just some blue shade in this case. Then we're calculating the diffuse color by the dot product from the light vector and the normal. If the dot product is below 0, no light hits the surface at this place. So we use the max function to pick either 0 or a positive value. And then we apply this factor to our diffuse color. This is the term for the specular light. We again calculate the dot product, this time with the reflection vector and the vector pointing towards us, the camera. And then we're using the power, and we have an additional parameter for the specular light, which we're using in the power calculation, which is called shininess, or an alpha value. So if we change this value, it changes how shiny the surface is, or how shiny it appears. So that's all there is to the light calculation. Here is where we specify our light parameters. We have to specify a position. Here I used a sign with the time parameter to move the light. We can place the light somewhere else if you want, for example, on the right side. Here we specify ambient, diffuse, and specular colors. And we can specify the shininess parameter. If we have more than one light, we could just add this up with to the color. Let's try this out. Now we can move the light into the other direction, and we get two light sources. So now we have light, but okay, before we get to the shadow part, Let's talk a bit about how we can construct a more complex scene than a sphere from this. And we can combine the different sign distance function with minimum or maximum to produce intersection, union, or difference, and build our scene with this. And if we use some special kind of minimum or maximum, some smoothed version of min and max, we can do morphing, like we can make a smooth transition from one object into another. To get an overview of how you can build a scene, I've included a list of sign distance functions where you can just pick out the sign distance function for primitives. There are a lot of primitives. You can move them around with matrix transformations since they're all centered. And you can combine them. Now let's look at the combination. In the morphing snippet. Okay. Okay, to give the credit to the one who deserves it, the link I pointed to with the sign distance functions and the function I'm using here, the smooth minimum, is written by Inigo Quires. If I pronounce the name correctly, I doubt he's ever going to hear this talk, but he's the creator of the Shader Toy website. And there's a lot of good articles on his website. And he's also posting on Shader Toy. I don't know where at the moment, but I'm pretty sure it's somewhere mentioned on his website. And you can just look up the code and use it in your own shaders. But back to the example. So we have this minimum function, which is a smooth minimum. And we have our scene distance function. I take the point we assigned in the main function and translate it in the y direction, in the positive and negative y direction for two different spheres. The translation function is the same we had before. And now we can combine this using the smooth minimum, for example. The simpler way to combine this would be to use a normal minimum function. Where we just have the two parameters. So if we don't use a smooth minimum, the transition is hard. So it's just a hard edge between the two spheres. But with the smooth minimum, we can do the morphing stuff. So in this minimum function, you can specify an additional parameter of how smooth you want the transition to go. If you pick 0, you have a hard transition again. If you pick 1, the transition is really smooth. And yeah, you can try experimenting with it. Let's try a max function, for example. So the max gives us the intersection. And we should get difference if... No. Okay. So this is how you can combine different distance functions. Now that we can combine geometry, we can insert some kind of bottom plane into our scene and cast shadows, which is kind of straightforward in ray marching because we get a lot for free. Let's try the shadow snippet. Okay. Okay, I think I put the shadow snippet twice in there. Or there's at least some other stuff that doesn't belong in there. Okay, so the shadow snippet's working. I'll check if I can update this really quick. Okay, so the shadow snippet on the website should be working now as well. So how do we calculate the shadows knowing the signed distance function? We can do the following. When we ray march our scene, we step into the scene until we hit a surface. And once we hit the surface, or if we hit the surface, we get a point on the scene. Now we have this point, and we have our light source. We know where our light source is. We have our light source position. And we can basically do the same algorithm again. We can just, instead of having us as a camera, we're using the point we hit on the surface as a camera, and it's ray marching towards the light source. Now, if we hit a surface on this way to the light source, we know, okay, we can't reach the light source from this point. So, if we can't reach the light source from this point, we know, okay, the view is obstructed and there has to be a shadow. And the K and the res value here are for additional beauty, which gives us some kind of smooth edges around the shadows. I've had problems messing around too much with those values. This works. Oh, this works actually pretty nice. It didn't work yesterday, but it seems to work today. For whatever reason. But yeah, this K value specifies how broad the shadow is. The higher it is, the more hard are its edges. And if you use lower values for K, you get some penumbra. So that's basically it for ray marching. Where you can go from here is you can pick some distance functions and build your scene and use the shadows and lighting techniques. And you can build some really nice scenes with this. Maybe I can show some on IQ's website. The author of Shader Toy I mentioned does some really cool stuff with signed distance functions. For example, everything in this scene is made by signed distance functions and connected with the minimum maximum functions. And you can do quite a lot just with signed distance functions. So you can do some really nice modeling with this. Now, as the last part, I want to quickly show how you can get some randomness into shaders with the 2D random snippet. Which again appears to be broken. Okay, the random sample should work now. We don't really have or need real random function or random functions or cryptographically secure random functions in shaders. We can just build some pseudo-random number generators. This one is taken from the Book of Shaders. Using the fractional part of floating point value, the sign, and the dot product for 2D random to create random values. You can play around with this to change the randomness values. This is also the random generator I used for the Balkan logo shader. And if you multiply the normalized view direction, the normalized fragment shader pixel, and you take the floor of this value, you can build some kind of tile map with this. You can just split the screen into 10 different parts. And if you supply the tile value to the random generator, you get something like looking like this. So this is basically how you would go with random values in shaders. What I'm not covering here is that sometimes randomness is just too random or not random enough. Just imagine having the same song twice in your playlist if you play it on random. which is in real projects, you could either use random in a smart way, or you can use some kind of noise or fractals. And I'm not dealing with fractals or noise here for now. So that's basically it with the actual coding. What I'm trying to get into now, going from here, is the demo scene. What is the demo scene? Originally, demos or graphics demos were from software crackers who would use it as some kind of signature intro for their cracks. Those are little self-contained programs doing visual effects like we did, and additionally using audio, which can be some really cool stuff. There are either non-restricted demos which just try to show the best of a graphics card, for example, what can you do. There are also size-restricted demos, 4K, 64K, which is about fitting the best demo in the smallest possible executable. And yeah, and it's not just OpenGL or something. You can do those demos on old machines, like a C64 is also a relatively popular platform for small demos. An example for a demo like this is Engage from Logicoma, which is personally one of my favorites. I'm not sure if sound will be working over HTML. No, okay. Then we'll just get the visuals, which is not as exciting, but you can see there's a lot more you can do with shaders than what I've shown, and it probably takes some years till you build the skill to build something like that. But the link is still in the presentation. You can watch it. It's pretty cool with sound. So what I've gathered so far, getting started with demos, I've added the links to the website. One cool resource is Ferris of Logicoma, going by the Ferris Tweets Now handle on Twitter. And he also streams demo-related stuff and emulator building on Twitch. He streams today. There's also research by, it would probably not be nice to pronounce his name because I'll probably pronounce it wrong, but I put the link in the, as well on the Shader website. A pretty good write-up on how a 64K intro is made. And also a GitHub page I found which is called Teach Yourself Demo Scene in 14 Days, which is obviously not teaching you the full stuff, but it's some kind of nice write-up. And thank you for listening so far.